Bismillahirrahmanirrahim. So today we will discuss first about the signals and I will talk about the digital signals. And I've already studied in signal processing course. A digital signal is usually represented like this, x of n. Let's say an example, maybe this is -1, 0, 1, 2, 6, 5, like this. And if I put an arrow mark here, this is the point where n equal to 0. Okay, and this signal actually it is a finite length signal. Finite length. The length of the signal you can say n is equal to 0 here, and 1, 2, 3, 4, 5. The length of the signal actually it is 5. Okay, this is the finite length signal. So all of you know that like this we can represent any signals. Okay, so you can represent a signal as a vector also. We can call it as a vector. A vector is a collection of points. Actually, you can represent a signal like this, the same signal, -1, 0, 1, 2, okay, 2, and this is 6 and 5. Okay, and this is nothing but a column matrix, or we will call it as a vector. And what is the dimension of this vector? Dimension of this vector, how many elements here? Sorry, what is the dimension? Sorry, here the length of the signal is 6. I have made a mistake here. This is the first value, this is the second value, third, fourth, 5, 6. So that what is the dimension here? The dimension n equal to 6. Is it okay? Dimension n equal to 6.
Yes.
Okay.
So we can represent a finite length signal by using a vector. Okay. Now, if the dimension is 2, can you tell me a signal with dimension 2? It is nothing but, let's say it is +1, and let's say it is 3. This is an example for dimension 2. That means it is having the first value, we can call it as x1 or x0, and the second value it is x1. So if I am representing in a plane, I can say this is my x0 and this is my x1, and the coordinate x0 and x1 actually like this. This is my x0 and this is my x1. So this is my vector. This point is nothing but it is 1 and 3. And what is x0 here? X0 equal to 1 and x1 is equal to 3. Do you agree with me in this regard to represent
Yeah.
like this?
Okay.
Now why I am calling this as a vector? Because you can represent like this as a straight line with some arrow and some angle with the first coordinate. So the first coordinate I can say this is my first coordinate. I can say that this is my x coordinate, or we can say this is my coordinate in the x direction, this is my coordinate in the y direction. So this is my coordinate in the x direction and this is my coordinate in the y direction. So what is the dimension of the signal here? How many coordinates are required for this signal? Dimension. Yes, the dimension is 2.
Doctor,
The dimension is, yes.
can be there more than 3 dimensions in real life?
Yes, there are situations. Okay, but it is not like in physics. Actually, in physics also there is 4th dimension. What is the 4th dimension in the physics?
I have no
Right.
idea.
You have x, y, z, that is the space. And what is the 4th dimension?
Time.
The height?
Yeah, time. Yes, time. Actually, the time is having. So I am not going to continue that discussion. It is a vast discussion. Okay, I'm quitting the here itself. Anyway, we will continue our discussion here on the dimension.
Okay,
Here
sir.
you can see in signal domain. I hope that you are convinced about my explanation, you can have more than 3 or 4 or any dimension, okay, in signal. Because
Yes.
if you have a signal -1, +1, 3, 4, 5, like this, suppose this is, yeah, -1, +1, like this, then what is the dimension of this signal? The dimension n equal to
5 dimensions.
5. Yes, this is 5. This is the dimension of the signal. But actually the dimension is having another meaning also. The dimension of a signal is having, because this is a vector representation of the signal is represented using a vector. This is represented using a vector. But it is having another meaning also. You can represent your signal using a set of functions. That means you can represent your signal by using a set of another signal. I am going to define something known as basis. You are familiar with this word by yesterday's lecture, basis. You remember?
Yes, yes.
Yes, sir.
Yes. I'm going to define the basis. My first basis is B0. I'm going to define the basis like this for the above signal. For this signal, I'm taking this example. 1 0 0 0 0. This is my first basis, and this is my second basis is 0 1 0. I will reduce the dimension for my, okay, that's it, okay, no problem. 0 0, and this is my B2. B2 is 0 0 1 0 0, and my B3 is equal to, what is it, 0 0 0 1 0. Do you agree with me?
Yes,
B0,
sir.
B1,
Yes.
B2, I think
Yes.
B0, B1, B2, B3, and B4, right? B4 is 0 0 0. These are all the basis function. So how many basis functions are there here? There are 5 basis.
5.
Yes, 5 basis function. Okay, please remember, I will rewrite my example again in this page. X is equal to -1, I think it is +1 3 4 5, right? +1 3 4 5. This is my signal, and I have the basis B0 B1 B2 B3 and B4. Okay, how many bases we have? How many bases? How many bases? We have 5 bases. Do you agree with me, right? And you know what is
Yes.
B0? B0 means, yeah, B0 means this is my position. This is my position here. This is my 0th position. This is my first position. This is my second position. And this is my third position. And this is my fourth position. These are all the position. Okay. Second,
Okay.
third. Okay. First. Now I can write my original signal X. I can write my original signal X as -1 multiplied with 1 0 0 0 0 plus +1 multiplied with 0 1 0 0 0 0. Sorry, I think 5 zeros are there. Total, yes, plus 3 multiplied with 0 0 1 0 0 plus 4 multiplied with 0 0 0 1 0 plus 5 multiplied with 0 0 0 0 1. Do you agree with me in this regard? I can represent like this.
Yes, sir.
Yes. Yes.
Yes. Now you can see this is my first basis B1, sorry, B0. This is my second basis B1, and this is my third basis B2, and this is my B3, and this is my B4. So I can decompose my original signal in as some coefficient. I can say let is A0. Let's say this is A1, this is A2, this is A3. I am going to generalize the concept A4. So I can represent any signal with this dimension 5 with the basis A0 into B0 plus A1 into B1 plus A2 into B2 plus A3 into B3 plus A4 into B4. Do you agree with me in this regard?
Yes,
Yes.
doctor.
Yes, sir.
Yeah. And what is this BI in general? BI means all are 0 except the ith position. That means the ith position will be equal to 1. Do you agree with me? BI means at the ith position it will be 1. Yes. So you can represent any signal x as a combination of small another functions, basis functions. So you know this BI we will call it as basis function. So I can represent my signal as AI into BI as summation I changes from 0 to
0
n
to
minus
4.
1. Yeah, 0 to 4. If it in general, if it is n dimensional, then it is n minus 1. Do you agree with me in this regard?
Yes.
Okay.
General.
Yes, sir.
So this is the basic idea. So you assume you have a very random signal like this, which is having a length. I am going to representing a continuous time signal like this. You can have a continuous signal like this. It is not one value. It contains how many points here? If you see the signal, how many points are there? This is a function of
Infinitely.
time. Yeah, you can see it is a function of time. It is infinite number of points are there. This is your signal X. You can represent this signal as the combination of many other signal, as the sum of many basis function. Okay, and what will be the basis here? You see the signal is continuous, so the basis also will be
Continuous.
continuous. But what about the coefficients, these coefficients, whether it will be continuous? It will be continuous or not? What about the coefficients?
Will be numbers.
It will be numbers. Sometimes it will be continuous also. Sometimes it will be discrete. You understood? It will depend upon the property of the continuous time signal. This is a continuous signal. It is a continuous signal. Okay, it is a continuous signal. So it will be this AI here, the coefficient can be discrete or can be sometimes can be continuous also. But there are some situation it become discrete, but in some situation it become continuous. What are those situation? I will explain later. Okay, I hope it is clear to you. This idea is clear to you. Yeah. Now you know you consider a linear system. I will explain with the digital system first. Okay, we will, because it is more convenient and it is more understandable to you. You have a system h of n and you give an input x of n. What will be the output? Output will be y of n, and y of n is nothing but x of n convolution h of n. This you have studied already, right?
Sure.
Yes, this you have already studied. Now you see what is this convolution y of n? Y of n is equal to, what will be? Summation x of n into h of n minus l. Okay?
Yes, sir.
Okay.
Yeah. H of n minus l. This is the basic equation. Okay? The summation x of n into h of n minus l. I will take a simple example, then it will be clear to you. Very simple simple example with the dimension 2. Let us assume that we have a system which is represented by, let's say it is 1 and 3. Okay. Now
Okay.
I have a input which is represented by maybe some 4 and 5. This is my input. Then what will be my h of x of n into h of n minus l? My y of n can be represented as y of 0, let's say n equal to 0. Then this okay, sorry, this I have made a mistake here. X of l into, you might have studied this one, x of l into
Yes.
h of n minus l. Yes, yes. Okay. Now what will be y of 0? Y of 0 is nothing but x of l. I will put my l equal to 0 first. L is changing from this length, l equal to 0 to l equal to 1. You see here how many values are there? 2 values. So 0 and 1. So I will put l equal to 0. That means x of 0 into h of my n equal to 0 here. N equal to 0. This is my n. N equal to 0 here, because this is my n. N equal to 0 here. Y h of 0 minus what is,
Minus
this is
0.
a signal which is starting from 0. Minus 0. Okay. Now I have to change for all L. Okay. L should varies from 0 to n minus 1, or whatever the length of the h. Okay. So 0 to 0, then plus, I will change the value of L. L become 1. When L become here, you see L equal to 0, and here L equal to 0. Now x of 1, that means L equal to 1 into h of 0 minus 1. 0 minus 1. Is there anything h of minus 1? Anything is there?
Yes.
No.
Is there anything? Nothing.
No, no.
No.
So h of minus
No.
1, because we are considering a causal system. We are considering a causal system. That means h of minus 1, nothing is defined. So it is 0. So y of 0, I can represent like this. X of 0 into h of 0. Do you agree with me, this one?
Yes.
Yes, yes.
Yes, sir.
Now I will find y of 1. Y of 1. I am going to find y of 1. What is y of 1 here? Y of
X
1
of 1.
means x of 0. I will start with x of 0 into h of n equal to
1
1.
minus 0
1 minus 0 plus
plus x of 1.
x of 1 into h
X
of
of 1 minus 1.
1 minus 1. Okay. Observe this carefully. This is not a simple thing. You will not get it from textbook. Any textbook you will not get this explanation. That's why I'm saying maybe it's very difficult to get the explanation like this. Y of 0 is equal to x of 0 into h of 0, and y of 1 I will write x of 0 into h of 1, x of 0 into h of 1, and x of 1 into h of 0, right? H of 0. Okay. Do you agree with me this regard?
Yes, sir.
Doctor, why we start with
Yes.
x0 and y1?
Yeah, our variable which is changing is L, not N. And this is N. Is it clear?
Okay.
You see here my y of n is having a formula x of L into h of n minus L, and it is changing over L. L varies from 0 to 1. So first you will put L equal to 0, then here also L equal to 0. And if you want to find y of 0, you will put n equal to 0. If you want to find y of 1, you have to put n equal to 1. Clear?
Okay. Okay, Doctor.
So I am going to represent my signal in terms of vector. What is what is x? I forgot. X is 4 and 5. 4 and 5. And what is my h? H is 1 and 3. 1 and 3. Now observe this carefully. My x can be written as x0, x1. Do you agree with me? This one?
Yes.
Okay.
Now I am going to represent this entire thing. That means our convolution. This is our convolution. This is the result of our convolution, right? This is the result of our
Yes, sir.
result of convolution. Yes. I am going to represent this property as a matrix. You know it is a matrix, and my output is nothing but y0 and y1, and this matrix I will call H because it is coming from the system, and this is X. So I am going to represent my output Y as H into X. You can see it is a symbol multiplication in matrix, or it is a linear multiplication. That's why we are calling it as a linear system. Then what will be the matrix H? Can you tell me? What is Y0 is nothing but X0 into H0. I will write like this, and this is 0. Is it okay?
Yes, sir.
Okay.
And I will write like this, H of 1 and H of 0. Is it okay?
Yes, sir.
Yes.
Yes. You see here, this is my matrix H. My matrix H is nothing but H of 0 and 0. And this is H of 1 and H of 0. Okay, this is my matrix H. And sorry, I will put here my x0 and x1. Then what will be my y0? This will be y0 and this is y1. Please tell me the equation for y0. Y0 is x0 into, no, just forget about the numbers. For this example, h0 into x0 plus 0
Multiplication.
into, yes, and this is y of 1 is h1 into x1 plus h0 into x1. Do you agree with me? This one, what I have written,
Yes.
is it
Yes,
same
sir.
as that of,
Multiplication.
is it same this equation, this one, and this equation and this equation, is it same?
Same.
Yes, Doctor. Same.
Yes, same. So we are representing the property of the system by using a matrix. So I am representing this thing as some y, and this is my x. So I can represent my system as h into x. Agree with me, this one?
Yes, sir.
Yes.
Doctor,
Yes.
is y1 the same equation of the previous one?
Let me check. Okay. Let me check. Okay. X0, yes. Okay, sorry, this is 0, and that is h1 into x0 plus h0 into x1, same equation. Okay, you can verify this because I have made a mistake here. So you can see here this will be same. So what is overall conclusion? If you have a system h of n and you have y of n and the input x of n, you can represent your y as h into x by using the matrix notation, by using matrix. I think you will agree with me in this regard. It's very simple thing.
So, yes.
Okay. Yes. Okay. So that is the property. But when you see the matrix, you have the system now H and you have the input now X, and you have the y, and y is nothing but h into x. This kind of notation is very important notation in literature. You can see if you read the papers, the research articles and all, you can see this kind of notations. Now I am going to take some particular inputs, not all inputs. If I give some inputs, let's say my input is a special input. If my input is a special input, let's say I am going to take an input I1. What will be the output? Y of I1 will be equal to H into I1. Do you agree with me? Instead of X, I am giving the input I1.
Yes.
But for some special input, not all input, for some special inputs, some special input, let's say I will not use this notation. This notation is a little bit. I have special input, then my y1 is equal to h into x1 bar. For some special inputs xi, let's say in general, I will get the output h into xi, but you can see your same input as the output, but it is multiplied with a number which is lambda I. This is one of the important property. I'll give you an example. Suppose you have a system and you give an input, let's say it is 2 and 3. Suppose your xi is 2 and 3. What will be the output? Output will be some constant lambda I, constant, not the matrix. Okay, your yi become, let's say this is yi, your yi become some constant into 2 and 3. Is there anything special here?
Yes.
That means if you have a vector like this, what will be the direction of the vector at the output? The direction of the vector at the output. Same.
Section with long magnitude.
But the magnitude will be, suppose this is having a magnitude, suppose it is having a magnitude is equal to, input is having a magnitude is equal to a, then the magnitude at the output will be how much? Lambda I into a. Do you agree with me? This is how it is transforming. That means
Yes.
if you give a special kind of input, it is not satisfactory for all. It will not satisfy for all input. There are some special input for some systems. Those inputs, if you give those inputs, what will happen? The direction of the input signal vector will not change, but it will be simply scaled by a factor. You understood?
Yes.
Yes, sir.
So if you give some kind of input, you will get the output as lambda I into xi. This kind of special inputs, these special inputs are called as eigenfunctions. So when you give eigenfunction to a system H, you will get lambda I into xi, the same thing. So you will get the eigenfunction at the output, which will not change, but there is a constant. It is a multiplication factor, and the constant we will call as eigenvalue. Have you heard about this term, eigenvalue, anywhere?
No, I'm not.
No? Okay.
I think
This is
I
one
heard
of
this
the
about eigen. This course, doctor.
in mathematics, that's what I'm asking.
Before some lectures.
Not this course I am asking. Have you heard in mathematics course in matrix? That's what I'm asking.
No, sir.
In matrix. So what is the property here? You see, this is a special input. If you give this kind of special input, you can see your eigenfunction at the output, but it is multiplied with a constant, and this constant we will call as eigenvalue. This is an important property which is used to characterize a system. Why it is important? Why it is important?
Because
I will
it
explain.
scales the magnitude.
Yeah, it is very simple thing. It will scale the magnitude. Why it is important? That is the question. I am going to explain this. Then you will get it. This very, very beautiful concepts. You can see here. Let us assume that you have a system H. Let us assume just an example. Okay, I don't know, there is some system H. Let's say my system is a matrix. Let's say it is a matrix 1 minus 1. Let's say 3 and 2. Okay, let's say it is 1 minus 1, 3 and 2. It is my H. Okay, let it be something. Okay, I will remove the values. It's better for me to explain. Let's say my eigenvector is x1. Then what will be my output? What will be my output?
y1.
It will be y1. How much? It will be, it contains x1
x1
and
is
it will be having a lambda 1 also, right?
Right.
Yes.
Yes. But this is also equal to h into x1. Do you agree with me?
Yes.
Yes. Yes, sir.
If you have an eigen function, all are eigenfunction. Please remember, all are eigenfunction. I am saying eigenfunction. This is a vector with two eigenfunction. Now y2 will be equal to lambda 2 into x2. How much? It will be h into x2. So you can see this is my output. Actually, this is my output. This is my output. Now, if I give another input which is not an eigenfunction, if you understand this concept, then it is clear. I am giving another input. Let's say my input is, let's say this is, sorry, I will use the notation x bar here. Sorry, x bar, x bar, x bar, x bar. Okay, x bar, x bar. Now I am giving another input. Let's say it is instead of x, please give me some notation. Let's say my input is z. What will be my output? Y.
Lambda z.
Not lambda z. It is not
HZ.
eigenfunction. Yes, it is just hz. Is not eigenfunction. Okay, not eigenfunction.
Yes, doctor.
Yes. Now I am giving. Now I will give some values for you to understand. Let's say this is something like 1 and minus 1. Let's say this is something like minus 1 and minus 1. Okay, these are all two. Let's say this minus 1 and plus 1. These are all two eigenfunction of the system. Yeah.
Is lambda 1 equals h?
Lambda 1 is not equal to h. Lambda
I mean-
1 is coming from the property of the h. Okay.
I
It
mean
is
from
not
that
equal
equation.
to. I will tell you. Okay, don't worry.
Okay.
It is not from the equation. You see, this is a matrix. This is a matrix, and this is a scalar constant. How it will become equal?
Yes, that's right.
But y1, the y1 you are getting by h into x1, and y1 that you are getting by lambda 1 into x1, both will be equal. That means if you calculate y1 equal to h into x1 bar, and if you calculate y1 is equal to lambda 1 into x1 bar, this both will be equal. You understood?
Yes.
Yeah, it is having a special property. That's what I'm saying you. So let us assume, this is just an assumption, there is some method to calculate this eigenfunction. There are some methods to calculate eigenfunction that I will explain to you later. not now, but assume that you have x1 and x1 bar and x2 bar, which are eigenfunctions. Now I have an input which is equal to let's say 3 and 4, which is not eigenfunction. It is not the eigenfunction. Then what will be my output? This is my question.
HZ.
For this,
H into Z.
for this, h into z, that you know, h into z, that will be the output, h into z. But I will use a trick here. I will represent, I told you how to represent a signal in terms of basis. I will represent my z in terms of x1 bar and x2 bar. I am going to represent. Is it okay?
Okay.
Okay.
Now I
sir.
am going to represent. How to
Okay.
represent the signal? Okay, I am going to represent, let's say my input, more simple. I don't want to complicate this. My input is, let's say my input is 1 and 0. Then it's very easy. How to represent my z in terms of x1 bar and x2 bar? X1 bar into some constant plus a2 into x2 bar. Please tell me the numbers. I want z, which is 1 and 0. a1 into x1 bar is 1 minus 1 plus a2 into x2 bar is minus 1 and 1. What will be the constant? a1.
It's gonna be 1.
a1,
Gonna be 1, sir.
let's say a1 is equal to 1. If a1 equal to 1 and a2 equal to 1, is it possible? I doubt. Is it okay? Please
A2
tell me
equals what?
what will be the, yeah, some number you want. You please give me the numbers.
Does it have to be a
a1.
number?
Yeah, it should be a number. a1 should be equal to how much? If I want this 1 and 0 on the left side, what should be a1 and what should be a2? I want 0 here. If I want 0, here it is minus 1 is the, is it possible?
Should we multiply it
Not
with
possible.
1?
Assume that, I will just substitute some random numbers here. I will just substitute here. Let's say this is by 2. Okay. And this is minus 1 by 2. It will not work, right?
Yes.
It will not work. I think so. 1 by 2 into 1 is 1 plus 1 by 2, 1 by 2. Then, yeah, it will not work.
Gonna be 1 and minus 1.
Yeah, 1 and minus 1.
Doctor, how
Yeah.
if we use a complex number as coefficient? Is it
No,
possible?
it is possible, but not now. Okay, I will explain the basics first. After that, we can go for the complex numbers. I am going to project it first. Okay, this is 1 and 0. This is 1 and minus 1. Excuse me, just wait. I'm going to represent. I think I will take another example. That's better for easier representation. I just want to explain the idea. The concept I will explain later. Other things I will explain the concept. The numerical methods for calculating it I will explain later. That's better. So let's say this
Okay,
is
sir.
let's say this is 1 and 1. That's better. Okay, this is 1 and 1. Then if it is 1 and 1, how to represent it? I will use here 1 by 2, and I will use here 1 minus 1 by 2. Is it okay? One and minus 1, let's say. Okay, what it will be? No,
Will
no,
it be
it
the
is not
same?
correct, right?
No, it will not.
No,
I don't
It
doctor.
think
cannot.
so.
Then how to find it? Please give me some answer for this. It can be complex number also, but I want an example with the numerical value. Just wait 1 second. Let
I
me check
think, doctor.
the basis I have given is correct or not.
Okay, sir.
Minus 1. Okay, this is the problem actually. The basis is having some problem. The basis, let me check. I will change the values because I have randomly chosen the values. That's the problem. You understood?
That's okay.
That is the issue. Since I have used the values randomly, then okay, I will use here this one. That's a better option. Okay, I will use the first eigenfunction 1 minus 1. Second eigenfunction is 1 1. Then I think it is easy for you to have any number. Let's say it is 1 2, 1 and 2, or okay 3 2. Let's say 3 and 2, 3 and 2, or 3 and 0, whatever it be. 3 3 and 0. Yes, 3 or 4. I'm sorry for this because yeah. Now
That's okay.
please observe. Now please observe the problem. You have the x1 1 minus 1 and x2 1 1. These two are eigen functions, and you have some arbitrary input. You have some arbitrary input which is z, which is equal to 4 and 0, and you are going to represent this input in terms of your eigen function. What it will be? It is 4 and 0. Then what it will be?
2, both of them.
Multiply by
2.
2.
Yeah, I can represent like this, right? 2 and 2. Is it
Yes.
okay? Yes. Now what is coefficient a1? A1 equal to 2 and a2 is equal to
Yes.
2.
Doctor,
Do you
why
agree
we
with me
multiply?
in this regard? Sorry?
Why we multiply with 2?
I want 4 on the left side. Please see this. I want 4 on the left side. If I want to, you see here, if I multiply with 2, 2 into 1 and 2 into 1, it become 4. Is it clear?
Yes,
Next,
doctor. I got
2
your
into
point.
minus 1 and 2, it becomes 0. You got it? So my coefficient is 2 and 2. There are some methods for finding this. I will give you later anyway. There are some methods for this. You can verify how we can find this. How we can find it. That means you take your z, you take the, how you are getting a1. To find a1, the method I will give you, you take your z, transpose the z and multiply with x1 bar. That means you have 4. After that, you divide it with the dimension. What is the dimension here? It is 2 cross 1. Yes, divided by 2.
2
Now you see, yes, 4 0, because it is the transpose. And what is x1? 1 minus 1. Then you will get it as how much?
2.
You will get it as 4 into 1 plus 0 into minus 1 divided by 2. This divided by 2 is there. So what is the answer? You will get 2. Do you agree with me?
Yes.
Yes.
Similarly, in the same way, you
Yes,
can find
sir.
A2. How to find A2? You will take your vector Z transpose into x1, not x1, x2 bar, and you will divide it with 2 because it is the dimension. So what it will be? It will be 4, 0, 1, 1. This divided by 2. Again, you will get A2 equal to 2.
2.
Do you agree with me? This? Yes.
Yes.
So this is
Yes,
how
sir.
you can find. This is the method to find. Okay, this is the method to find. Now you can see my Z. My Z is equal to A1 into x1 bar plus A2 into x2 bar. I think you will agree with me in this regard, right?
Yes.
Now I am passing this Z. I am passing this Z through my linear system. My linear system. Very, very careful. Linear system. What is a linear system? A linear system will obey the principle of superposition and homogeneity. You understood?
Yes.
Then what will be the output? Y equal to H into Z. Do you understood?
Okay.
Okay.
Yes. Now what is Y? Y equal to H into Z, which is nothing but H into, what is my Z? It is A1 into x1 bar plus A2 into x2 bar. Is it clear?
Yes,
Yes.
sir.
Yes.
So this is equal to H into A1 is a constant. So you can write it first because it is a constant. It is a constant. So you can write A1 is a constant, scalar value, H into x1 bar plus A2 into H into x2 bar. Do you agree with me?
Yes, sir.
Yes.
Yes.
But these two are eigenfunction. You know this. So for eigenfunction, H into x, it is nothing but A1 into lambda 1 into x1, x1 bar. Do you agree with me?
Yes.
I have already told you
Yes,
for
doctor.
eigenfunction, it is a
Yes,
scalar
yes.
multiplication. A2 into
Yes.
lambda 2 into x2 bar. So I will give you, this is the output. You see here what is, if we represent our original function in terms of my basis, you can say this is my basis function b0 and this is my basis function b1. So I am going to represent my signal in terms of eigenfunction. This is eigenfunction and this is also eigenfunction. If I represent my signal in terms of eigenfunctions, then I easily find out what is the output in terms of eigenfunction. Do you agree with me in this regard? This is the very, very important point.
Yes.
That means
Yes, sir.
if you have a space, I will draw in vector. If you have x1 bar like this, and if you have x2 bar like this, you have some point z, there is some point z, that z is pointing like this. So across the direction of x1 bar, the coefficient is a1. Across the direction of x2 bar, the projection is a2. Do you understand what I am representing? This one?
Yes, doctor.
Yes,
Yes.
yes.
So what is Z? Z is nothing but A1 into X1 bar plus A2 into X2 bar. Now, if I pass, this is very, very beautiful concept. If I pass this through a system H, you will get the same X1 bar, means if you give X1 bar, the output will be lambda 1 into X1 bar. If you give only x2 bar, the output will be lambda 2 into x2 bar. But for this particular input, you will get a1 multiplied with lambda 1 and a2 multiplied with lambda 2. According to a1 and a2, you will get your output y something like this. This is your y. your y will be equal to a1 into lambda 1 into x1 bar plus a2 into lambda 2 into x2 bar. Do you agree with me this representation?
Yes, doctor.
Yes, this is the beauty.
Yes.
So if you represent a signal by using basis function, what is happening? You are actually simplifying the things with a simple multiplication. You understood?
Yes, doctor.
So
Suppose
the benefit
you have
is to make it simple.
yes, something is actually if we are using eigenfunction, if we use eigenfunction, I am going to generalize the thing. Let's say x1 is an eigenfunction, x2 is another eigenfunction, x3 is another eigenfunction, x4 is another eigenfunction. If you have an input z which is a1 into x1 bar plus a2, or okay, in general I will say x4 up to xn, and if you have an input z equal to summation I equal to 1 to n, okay, ai into xi bar. If this is your input, you pass this input through the system h, and these are all eigenfunction, and you are representing your original signal using eigenfunctions, and you will get the output as summation I equal to 1 to n. Each ai will get multiplied with lambda I into xi bar. This will be your output. Do you agree with me this representation?
Doctor.
Okay.
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 Yeah, I hope that it is clear, very clear. I think so. You know the
Yes,
summation
sir.
and matrix. Yes, this is the beauty. You are representing a signal in terms of another signal. Now I will come to the Laplace. I am talking about now the discrete time signal. In Laplace transform, our eigenfunction in Laplace transform is a continuous function which is e power st. It is the function. This function is our eigenfunction in Laplace transform. This is an eigenfunction. I will give you the explanation. You know the continuous time convolution of the system. Continuous time convolution. What is the equation for continuous time convolution? You have a system
Integration.
x of t, and you have the system h of t, and the output will be y of t, and y of t will be equal to how much?
X of t convolve h of t.
Yeah, h of t convolve h of t. You can represent in two different ways. One is
Integration from minus
integral from
infinity.
0 to infinity, integral 0 to
From minus
infinity
infinity.
x of, yeah, because I am talking here about the causal systems. Okay,
Okay, sir.
for causal system, for t less than 0, the function will be equal to 0. Okay, I'm
Yes,
talking
sir.
about the causal system. Real-time systems are causal. Other things are just imaginary for mathematical things. So h of t minus tau d tau. Now I am going to give my function input e power st. Be very careful. You see here, I am going to give my input as e power st. This is my input. I told you it is an eigenfunction. If it is an eigenfunction, I will get the same function at the output. Do you agree with me in this regard?
Yes,
Yes.
sir.
Yes.
I am going to check it. Is it an eigenfunction? If it is an eigenfunction, I will get the same thing at the output. Now, you can see I can represent the convolution in different ways. Another way is I can represent like this. H of t minus tau into x of tau d tau. Both will give you the same results. You might have studied because x of t convolution h of t is equal to both h of t convolution x of t. Okay, this is a property of the
Yes,
convolution.
sir.
Okay,
Yes.
if you change the order, it will give you the same result. Now you see, I'm going to give my x of t as e power st, and this is my system h of t, and I'm going to calculate the continuous time output of the system, and my output is nothing but integral 0 to infinity x of tau. Sorry, I will use the second representation. I will use h of tau into x of t minus tau, and I am integrating with respect to tau. Now this is equal to this output. So y of t will be equal to integral of 0 to infinity h of tau. What is x of t minus tau? E power s into t minus tau. Do you agree with me?
Yes, sir.
D tau.
Yes.
Yes.
So you can see here integral 0 to infinity h of tau. You see the variable tau e power s into t multiplied with e power minus s into tau d tau. I am integrating with respect to what? With respect to
Tau.
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 So I will take only the variables tau. Other variables will be a constant, right? Other variables will be a constant. Will be
Yes,
constant.
will be outside.
Yes.
Yeah. So I can take my e power st outside, and this 0 to infinity h of tau into e power minus s tau d tau. Do you agree with me? Is it okay what I have written?
Yes, sir.
Yes.
So this is nothing but e power st. And what is this guy I have told yesterday?
This
Laplace.
is
It is the
It's-
Laplace transform of h of tau, h of t, right?
yes. Right.
It is
Okay.
only the variable is different, tau, but the final after integration you will get the variable in s. So it is nothing but h of s. Do you agree with me?
Yes, sir.
Yes.
So
Yes.
my
Yes.
y of t, so you see here in y of t, what is there in y of t? In y of t, you can see my eigenfunction. Eigenfunction is repeated. Remember, in the previous example, you see here, in the previous example, I told you, if you give, you see, this is the eigenfunction, and what is this lambda? Lambda is the eigenvalue. Remember?
Yes.
Yes.
Now, can you tell me what is the eigenfunction and what is the eigenvalue here? Eigenfunction is
EST.
eigenfunction
E power
e power st. What is the eigenvalue?
H S.
Laplace.
Hs. It is nothing but the Laplace transform. So Laplace transform of a system will give you the eigenvalue of the system. Is it clear?
Okay.
Yes, sir.
Okay.
Now I am going to take some arbitrary input. After that, you see, I am going to take, there is a system. If I give my x of t, which is equal to e power st, I will give my output. What will be my output? H of s multiplied with e power st. What is this? It is the eigenvalue. And what is this? It is the eigenfunction, right?
Right.
Yes.
Right. Now I take another input, z of t, as I told in the previous example in the discrete time. I take my z of t, which is nothing but a1. It is nothing but uh, a1 into e power st. What will be my output?
A1. E of
A1
S
Into H of S
because it's linear.
yes, e
into
power
E
st.
power S.
Is it simple?
Yes, sir.
Now, and what is this guy? What is A1? A1 is nothing but, you see, what is h of s? H of s is nothing but the eigenvalue. So what is A1? A1 is the eigenvalue of what? Of z of t. Do you agree with me?
Yes.
So A1 can be a function of s also. If it is A1 is a function of s, then I can include here also a function of s. Is it okay?
Yes, sir.
Okay.
So what will be the output of the system here? You see here the output of the system, it is nothing but, if you represent by using e power st, the output of the system is also in terms of e power st. This is the beauty of Laplace transform. So if you are giving z of s, which is nothing but the eigenvalue of z of t, eigenvalue of z of t, you will now talk about eigenvalue only. I will use the next page, that's better. Now you have h of t, which is having the Laplace transform h of s. H of s is nothing but the eigenvalue of this system, and it is understood that it is understood that eigenfunction in Laplace transform is always, what will be the eigenfunction in Laplace transform?
E power st.
AST.
Yes, e power st. In Fourier transform, you have studied Fourier transform sometimes. I don't know how much it is covered. In Fourier transform, what will be the eigenfunction in Fourier transform? In Fourier, have you studied Fourier transform?
Yes, but I don't remember the function.
It is e power j omega. Okay,
Yes, yes, sir.
and here you see sigma
AK.
is, sorry,
Excuse me.
and here it
J
is
omega AK.
e power j omega t. Okay, e power j omega t. It is the in the Fourier transform. I am not talking about Fourier series. Fourier series is having another eigenfunction. Okay, small,
Yes, sir.
slightly different. So if you change the eigenfunction, you will get a different transform. You understood?
What did you say, doctor?
If you change the eigenfunctions, you see here in Laplace transform, the eigenfunction for Laplace transform is, function is nothing but e power st. And what is s? S is nothing but a complex number, e power sigma plus j omega. Is it clear?
Yes, sir.
Yes.
And what is this? What is this sigma plus j omega? Sigma is a complex plane, and this is j omega. It is a complex plane. We will call it as S plane. Okay, S plane. But if you put sigma equal to 0, then what will be S? S become,
J omega.
Totally imaginary.
J
it
omega.
become purely imaginary. Then we will call it as Fourier transform. It is a special case of Laplace transform. You understood?
Yes, sir.
Okay.
That means if I evaluate only along the imaginary axis, if I evaluate the Laplace transform, evaluate Laplace transform only on imaginary axis, then we will call it as Fourier transform. This is very, very important point. Don't forget this point, okay? So it is a special
Okay,
case of Laplace transform. Laplace transform is superior, and Fourier transform is the special case of Laplace transform. Now, I told you if you have x of t as a system, you will get y of t. If you give e power st, you will get some h of s into e power st. if you take the Laplace transform of x of t, Laplace transform means you are finding the eigenvalue. I told you it is the eigenvalue. I'm representing the Laplace transform x of s. What will be the output here? What will be the output?
H of
If
s
I am taking the
multiplied by x of s.
yes, so you see here, I don't need even, I am not talking about this e power st now. E power st is here, e power st is here. It is understood already. It is known to
Multiply
us.
by a of
We don't
s,
need
doctor.
what?
Multiply by a of s.
Not a of s here. Instead of a of s, I am using x of s. Instead of a of s, I am using x of s. X of s is my eigenvalue. In the previous example, you might have the confusion. This is the eigenvalue. Eigenvalue of z of t, we will call z of s. So a of s, I will say in general, this your a of s is generally called as the eigenvalue. That means it is nothing but your z of s. You understood?
Yes, sir.
So I'm going to conclude for today with last slide. That means that if I have any signal, I can find the eigenvalue corresponding eigenvalue of it with respect to my e power st. E power st is my basis. If I want to find the eigenvalue, I need a basis. So e power st is my basis in Laplace transform. Then if I find the eigenvalue, I will get x of s. So what is the convention for finding x of s? It is nothing but integral 0 to infinity x of t into e power minus st dt. Is it okay?
H of s, doctor. Eigenvalue.
Sorry? Yes, yes.
You mean h of s, the eigenvalue?
Yeah, for the signal, for system h of t, what is the corresponding eigenvalue? Eigenvalue with respect to basis e power st. What will be the eigenvalue?
HS.
H of s, the Laplace.
H of s. So what is happening here in a system? If you have a system h of t and input x of t and y of t, you forget about e power st. It is understood because we are talking about Laplace. So because it is understood, so what is the eigenvalue here? X of s. What is the eigenvalue for the system? H of s.
HS.
So output, the eigenvalue of output will be how much? This is the eigenvalue of output. It will be nothing but multiply
X.
these two eigenvalues.
Multiplication.
Yes, this is same thing you can see in the previous case. In discrete time, you can see I have already told you in the discrete time.
Oh, yes. I'll get you, doctor.
You see
I'll get
here
it.
multiplication. Yes, this is the multiplication. You see here simple multiplication. And this basis is understood in Laplace. In Laplace, this is the basis. In Laplace, the basis is e power st. We are not going to change. So we do not need we do not need to say every time e power st. We don't want to say every time. It is already understood. Understood?
Yes, sir.
So in Laplace domain, actually, we are finding, we are just multiplying, we are playing with the eigenvalues of the system. Instead of a complicated system, we are just playing with the eigenvalues. You understood? This is eigenvalue of
Yes,
x
sir.
of t.
Yes.
And this
Doctor,
is the eigenvalue of h of t. Yes.
x of s is the
Yes.
eigenvalue or eigenfunction?
It is not the eigenfunction, it is the eigenvalue, because Laplace, x of s is the Laplace transform. Laplace transform is
Uh,
always the eigenvalue. I have already told you. You see here, this one. What is this? H of s. It is eigenvalue. So the Laplace transform is the eigenvalue of the function of any function. It is the eigenvalue of any function. But what is the basis? Basis is e power
ST.
st. That is the basis. That you should understand. I hope that this is clear to you, right?
Yes, doctor. That's the uses of Laplace transform to find
Yeah.
eigenvalue.
So you see here, even though we have a very complicated signal, we will just transform it into eigenvalue, and we can play with the eigenvalue. So in automatic control system, you can predict about the stability of the system. You can find the transient response of the system. You can find the steady state response of the system. Everything becomes very simple in terms of eigenvalue. The signal will be very complex. It will be changing like this, very fast changing signal. But the eigenvalue will be a function. You can easily evaluate it, and based on this eigenvalue, you can design the system. You understood? That is why we are using the Laplace transform. And your S is nothing but sigma plus j omega. Now, if you put sigma equal to 0, you are going to evaluate the Laplace transform only on imaginary axis. Then, if you put sigma equal to 0, then x of s with sigma equal to 0 means it become x of j omega. Is it clear? It become x of j omega. And
Yes,
this we
very
will
clear.
call, it is known as Fourier transform. So in Fourier transform, what is the eigen function? Eigen
F bar j
function.
omega t.
Yes, in Fourier transform, in eigen function in Fourier transform, I will trust ft is nothing but e power j omega t. Is it clear?
Yes, doctor.
Okay.
So this is the simple way I can tell you. Inshallah, I will continue in the next class. I will give you some well-known Laplace transform, and we will do some problems on steady state analysis by using this concept. So please
Inshallah.
read this very carefully. You can read more articles. This basics is enough for you to read for further reading. You can read some articles in the internet, and you can understand more. If I am taking a course on Laplace transform, I think it needs at least 10 hours. That's why. So that's why I concluded within 1.5 hours. So inshallah, we can continue in the next class. I think you got some idea, right? Laplace transform.
Yes,
Sure,
doctor.
sure.
And what is basis function? What is eigenfunction? Eigenfunction is very, very important thing in linear system theory. We are talking about network theory. Network theory means we are talking about linear networks. In control systems, also we are talking about linear control systems. You are going to study. There are something like non-linear networks, and there are something like non-linear controls also. But in non-linear systems, it is not applicable. This kind of theory is not applicable. There is another theory which is known as state space approach, and it is known as state space approach. So we will model the system in state space approach, and this state space approach is the modern control theory. We will say it is modern control theory. So, but this kind of thing, what you are seeing now, this is the classical theory. And you know, the Fourier had made this theory. Excuse me, can you hear me? Right?
Yes, we can.
Yeah. Yes, the scientist Laplace had made the Laplace transform, and the Fourier has made the Fourier transform. It is the name of the scientist. All these are name of the scientist. It is made in 1800. You know, 1800. Fourier has made Fourier transform in 1800, some 1840 or something like that.
Yes.
Understood? But nobody knows what is the use of it. So it was kept in the literature for 150 years without any use. Understood?
Yes, doctor.
Yes.
Nobody used it. Nobody was knowing to use how to use this. What is the application of this? They have no idea. So around 150 years, it was made in 18500, and it was there till 1900. I think around 150 years, it was just kept in the book, and nobody read it. And when the communication systems, communication systems, our modern communication systems, when the theory of the modern communication systems developed, they want to know about the frequencies. Then they find that this Fourier transform is a lot of application in designing the communication systems. That is why we are using the Fourier transform widely in designing the modern communication systems. And also the Laplace transform, they find that it is having lot of application in advanced control theory. That's why we are using in automatic control. Okay, I hope that you got some sense of the transform theory. There are a lot of transform according to different basis function. Now in Laplace transform, our basis function is e power st, and in Fourier transform, our basis function is e power j omega t. If you can make a new basis, you can write a paper, research article, and you have to prove a lot of applications are there. So if you are making a new basis function, then you have a new transform. You understood? Usually we will call this, usually call this kind of basis as the kernel. The name is kernel. Okay, this basis we will call it as kernel. So if you define a new kernel function, you can come up with a new theory. Okay, I hope that this is clear. This is for today. I think this is enough. Inshallah, in the next class I will revise some few Laplace transforms, and after that we will do the problems on steady state analysis. Okay, Assalamu alaikum.
Okay, sir. Thank you. Alaikum salam.
Alaikum salam.